Hello. Hello.
Hello, sir.
Can you hear me?
Yes, sir.
Good. Thank you. Let's continue. So when we're talking about the oxidation of primary alcohol, we said it will give us an aldehyde, and from an aldehyde, uncontrollably it will go to carboxylic acid. But if we are selectively aiming to just get your aldehyde and stop there is a selective oxidizing agent that you can use that as it's converting to aldehyde, it will just tell that reaction, I don't want you to go to carboxylic acid. That's why we call it selective oxidizing agent. We call it pyridinium chlorochromate, which is simply called PCC. Please note those ones against your TME and your exam time. PCC is an acronym for pyridinium chlorochromate. When we are going to look at the first topic for next week, you will get a better understanding when we create the class for that last week that you missed. But this topic 2 must be for this week. And that's why we must not miss anything, because once we miss, we go to the next thing, we go to the next thing, and now come back if you have time to do the previous one. So PCC will help you to convert primary alcohol to aldehyde and stop there. It will convert it for you and it will stop there. So, but secondary alcohol will be oxidized. The major oxidizing agent that we use is sodium dichromate in acid. It will give you, or you can use chromic acid. It will turn a secondary alcohol to a ketone, and the reaction will stop there. Ketone will not go further. Ketone will not go further. In the reaction, ketone will not go further. This is an example A. You can see the A. You can see the example in A. The example in A is using this cyclic secondary alcohol to give us cyclic secondary ketone. If you look at the B is also a ketone, it's also a cyclic ketone. Now, when you want to know whether it's a secondary ketone or not, this edge of every of your angular thing are made up of carbon. This is a skeletal representation. If you remember your chemistry 102, there are various ways to represent organic compound. You can represent it in carbon-hydrogen form. You can represent it in carbon skeletal form. You can represent it in condensed form. So all these edge are carbon. So if this is a carbon that carry the OH, is the carbonyl carbon. And this carbonyl carbon, look at direct link. Is linked to a carbon here directly. Is linked to a carbon here directly. But it's linked the third one to the hydrogen and the fourth one to the OH. So with the carbonyl carbon is linked to two other carbon. What class of alcohol is that? Secondary alcohol. That's why when it's going here, even the oxygen is one here, the oxygen is one here, but the number of hydrogen has reduced. So this is an oxidation process because it's the removal of these two hydrogen, 1 and 2, to convert oxygen carbon bond to a double bond 1. So that's talking about the oxidation of secondary alcohol. Then when we're talking about the third class of alcohol is third type of alcohol is called tertiary alcohol. In tertiary alcohol, the carbon of the carbonyl is linked to 3 other carbon. If you look at this now, they say if our alcohol has 1 or more hydrogen on its carbonyl, there is a base catalyzed elimination that can occur. That's a condition. But now, if you are this, next week, if you have watched the video, it will make the class very interesting because you will have known a lot of things. We will now be solving problems. So the secondary alcohol is that. Tertiary alcohol Oxidation of tertiary alcohol is not possible because tertiary alcohol, the carbonyl is already having 3 carbon around it. So there is no loss of hydrogen that can be possible because it doesn't even have any hydrogen next to him. And there is no increase of oxygen that can be possible because it has already the oxygen of the alcohol. So the tertiary alcohol cannot be oxidized. So let's note that if they give you a tertiary alcohol, it cannot be oxidized. All it can do is to form a complex with the oxidizing agents. So under the conditions such as the tertiary alcohol do not generally react because tertiary alcohol has no hydrogen attached to the carbonyl. You remember oxidation has to do with removal of the hydrogen that is attached to the carbonyl. Then you have having oxidation. But in a tertiary alcohol, let's look at it. Out of the 4 bonds of the carbon in a tertiary alcohol, the first bond is linked to OH that makes this carbon to be called carbonyl. The other 3 bonds that are linked to him are linked to carbon. And you remember that oxidation means removal of hydrogen. So there is no hydrogen directly attached to our carbonyl carbon. So what will you remove? That's why we are saying tertiary alcohol cannot be oxidized because what you are doing is removing of hydrogen on your carbonyl. If you have primary alcohol, you have excess of hydrogen to remove to form aldehyde. If you have secondary alcohol, you have 2 hydrogen to remove to form ketone. But if you come to tertiary alcohol, this carbonyl carbon that I circled, you can see that there is no direct attach of hydrogen to it at all. Here is attached to carbon, here is attached to carbon, here is attached to carbon. Even the hydrogen of its hydroxyl group is attached to oxygen, not to carbon. It's the oxygen that now attached to carbon. So there's no oxidation that can take place in this. So let's note key word today. Excuse me, is that primary alcohol will oxidize to aldehyde and uncontrollably further oxidize to carboxylic acid. So if you are dealing with methanol, methanol will oxidize to methanal, and methanal go further to methanoic acid. But if you don't want the aldehyde part to go further, there's only 1 or 2 selective oxidizing agents you can use, which means primary alcohol going to aldehyde, you want it to stop there. Oh, I've taken the methanol and I've converted it to methanol, but I don't want it to go to methanoic acid. You will use PCC, which is pyridinium chlorochromate. It's prepared as a complex, pyridine. Pyridine is like a benzene ring that has one of its 6 carbon of benzene turned to nitrogen. This is pyridine, reacting pyridine with chromium trioxide, chromium and 3 oxygen, plus hydrochloric acid is what you use to prepare PCC. So this one will end up giving us the pyridine now exceeding its valency to become pyridinium, which is positively charged. You know, it already has 3 bonds around this nitrogen. So you use the 4th bond to bond with chromium and that oxygens and 3 oxygen. So that makes this one to positively charged center. And for every positively charged center, there must be a negatively charged chloride anion that comes because the chloride is coming from this hydrogen part to form that. So that's why we call this is what is called pyridinium, from the word positive charge for pyridine. Those are when you have sodium, it's a positive charge. When you have any positive, you have ion. So pyridinium chlorochromate. So we form the complex of that with HCl coming out of this. So let's note that. Class activity 1. Let's quickly look at this. What reagent selectively convert primary alcohol to aldehyde? Can somebody tell me? What reagent with selectively convert primary alcohol to aldehyde? That means what oxidizing agent can make primary alcohol to go to aldehyde and make that reaction to stop there, not allowing it to go to carboxylic acid or alkanoic acid further. What selective oxidizing agent that we use? Can somebody help us to attempt that?
PCC, sir.
Hmm? You said? What do you say? Hello? Hello? Can somebody help us?
PCC.
Very good. PCC. So they say with support your answer with a chemical equation. That's what I just finished doing. Pyridine plus CrO3 plus HCl, giving us that complex. That's simple. Number two, that's very good. Thank you for that attempt. Number two, type of alcohol in which all available hydrogen on the functional carbon are completely removed through oxidation is named dash. And the final product form is referred to as dash.
Tertiary alcohol.
A type of alcohol in which all the available hydrogen on the functional carbon are completely removed.
Tertiary
All
alcohol.
the hydrogen on the carbonyl carbon are completely removed. If the hydrogens are not there at all, then you know that's a tertiary alcohol and it cannot undergo oxidation, right? But here they are saying if you have all of the hydrogen completely removed, all the hydrogen attached to that carbonyl are completely removed. A type of alcohol in which all the available hydrogen are completely removed, leaving only the oxygen. What type of alcohol is that? And after they have been removed, what kind of final product is going to be formed? Okay, let's quickly go to my explanation. This is a primary alcohol. We have seen that your carbon is linked to only one more carbon. All others are hydrogen. This is a primary alcohol. Now, when you oxidize this primary alcohol, what happens? Out of the 3 hydrogen, 2 are removed. 1 removed from the oxygen, 1 removed from the carbon to form double bond. But there is still 1 hydrogen remain in this product. So a primary alcohol is not a type in which all of the hydrogen that is available on its carbonyl is removed. Because out of these 2 hydrogen, after the final product, 1 of that hydrogen is still retained. Out of these 2 hydrogen on the carbonyl, after it has been removed, 1 of it is still being retained. So it cannot be primary alcohol that we lose all of its hydrogen atom on the carbonyl atom to form the product. It's not primary alcohol. Let's go and check whether it is secondary alcohol. Let's go to secondary alcohol. Let's look at this secondary alcohol. In this secondary alcohol, this is, of course, our carbon. Every angular edge like this is a carbon. This is a carbon. This is a carbon. This is a carbon. Where there is hydrogen, they will state it. Now, this is a carbon of a carbonyl that has itself linked to 2 other carbon, 1 and 2, and 1 hydrogen. So this is a secondary alcohol. Now, in this secondary alcohol, there are 2 hydrogen attached here. 1 from the OH, 1 is directly attached to the carbonyl carbon. When you do the product finish, the carbonyl carbon has now 4 bonds. 1 here, 1 here, and 2 here. It's already completing its tetrahedral, and there's no more hydrogen on him. So in this case, this is an alcohol in which all the hydrogen attached to the carbonyl has been completely removed to have only C double bond O, no more hydrogen. So the answer to that question, the alcohol of its hydrogen available on the carbonyl removed is a secondary alcohol. And the oxidation of that will give us a ketone. That's what you see here. Let's look at another secondary alcohol. You see this carbon? It has an hydrogen directly attached to him. After the oxidation, the hydrogen of the alcohol is removed, the hydrogen attached to him is removed, and it turns to C double bond O. You can see C double bond O. So this carbonyl carbon no longer have any hydrogen. So this secondary alcohol is one in which the hydrogen attached to the carbonyl is completely lost to form this product. So in a secondary alcohol, under the processing of its oxidation, all the hydrogen linked to that carbonyl or available on the carbonyl will be completely removed, and that will help to form the product called ketone. But in primary alcohol, you will still see at least one of the hydrogen attached to your carbonyl of aldehyde. That's why we said primary alcohol leads to aldehyde carbonyl, secondary alcohol leads to ketonic carbonyl. Okay. So let's look at the question 2. So there's no problem with this question again. So the second one is transformation of the arine. That arine means aliphatic attached to a benzene containing compound. So benzene ring is rather stable to oxidizing agent. You cannot do addition reaction and say I'm adding hydrogen to benzene the same way you will have added hydrogen to alkene. Alkene and benzene are not the same. That's why both of them have C double bond C. The C double bond C in benzene is that 3 of those double bonds are conjugatively arranged in this manner: double, single, double, single, double, single. So relatively, the 3 double bond in benzene is far stable, much more stable than the double bond in alkene. In alkene, there can be addition of hydrogen to go from double bonds of alkene to single bond of alkene. But you cannot do that for benzene ring because it's in a ring system that is very stable. So addition of hydrogen to this cannot work. That's the uniqueness of benzene and benzene compound. However, if there are aliphatic group like CH3, C2H5 that are attached to your benzene ring, something can happen to those aliphatic group. So when you have this, for example, we have methyl benzene, 4-nitromethylbenzene, and methylbenzene is also known as toluene. A benzene that have a methyl group attached to it is called a toluene. So if you want to name this compound, this is 4-nitro, because nitro means NO2, and it's in position 4 to the origin. Methylbenzene origin is 1, 2, 3, 4, 5, 6. So this is methylbenzene is toluene. But in position 4 to that methylbenzene, if you use it as a parent, this is what you are saying. This is methylbenzene, which can also be called toluene. On the position 4 to that toluene, you have a nitro group. So this is called 4-nitrotoluene. 4-nitrotoluene. Because as you are knowing this thing, you should be knowing their name. In case they give you a name form, you must draw it in structure form. So when you see that, another way to name it is that if you don't want to use numbering, you can use the word form. And the word form is that once you identify the origin carbon in your benzene, this is the origin carbon because it's one linked to the methyl that make us to call it toluene. So position next to it, which is position 2, if you don't want to call it 2, you can call it auto, which is abbreviated as O, auto. The one that is third position or meta position to it, as Yoruba man will say, is called the meta position, which is abbreviated as M. And the one that is on position 4 to the starting point is called para. It's abbreviated as P. So if you don't want to call this one 4-nitrotoluene, you can also call it para-nitrotoluene. So in the sense that oxidation cannot happen in the ring system, but there is an alkyl group attached to it. Aliphatic methyl group on a benzene ring will be oxidized by chromic acid to turn it to carboxylic acid functional group. CH3 now becomes COOH. Why do we say it's oxidation here? We say it's oxidation here because one, in the CH3, there is no oxygen, but in the final product, you have added 2 oxygen. That satisfies it. Another thing that satisfies it, in the starting material, you have 3 hydrogen, but in the product, you have only 1 hydrogen. So you have this one fulfill removal of 2 hydrogen. It also fulfill addition of 2 oxygen. So both definition is quite obeyed in this reaction. The transformation of arine. Arine, I've said it before, that arine is just like benzene containing compound. It must have benzene. In addition to that, have some things attached to it. If there are nothing attached to it, you can just call it benzene. But when they say arine, it means it can be benzene or benzene-like compound in nature. So sodium dichromate in sulfuric acid or acetic acid is a common laboratory procedure. But aqueous nitric acid and potassium permanganate have also been used. That's after we have used the sodium dichromate here in acid, you can also use aqueous potassium permanganate. You see that you are getting the same desired result. In this one now, you discover that it's CH3 on a benzene ring. If you want to name this, let's try. If you have already said CH3 on benzene ring, make it methylbenzene, and that makes it toluene. That means this thing I'm circling is toluene. But outside of that, there's another substituent that is attached to it. You have to account for that. This is the origin, 1, 2, 3, 4. So when you look at this, then you can say that this is 2-chlorotoluene because it's a toluene that have chlorine on the position 2 to him. That's if you want to use figure numbering. If you want to use alphabet numbering, on position 2 to the origin is called the auto position. So that's what is abbreviated as O here. So autochlorotoluene and 2-chlorotoluene, you are talking the same thing in these different languages. So we're saying here that the same way the CH3 of the previous one was converted to COOH by the action of sodium dichromate in sulfuric acid. If you are trying to use aqueous potassium permanganate under heating, it will still the same methyl group converting to the other, which is carboxylic acid group. So it's still an oxidation reaction. I want somebody to help me to name this compound. What's the name of this compound? Can you see it? Can you see?
Yes, 3-bromotoluene.
3-bromotoluene. Irene, is that Irene?
Yes, it's Irene.
Very good. That's 3-bromotoluene. That's very good. I'm encouraged. Thank you very much. If you don't want to use the figure, which is 3, and you still want to name it using alphabet, what will you have called this compound? Will Agatha try?
Para-bromotoluene.
Wow, you tried. But I won't give it to you all. I will tell why. Do you want to know why?
Yes, sir.
Because I said the methylbenzene is this place, right? So the first carbon in the benzene will be this. And you start counting from there. This is 1, this is 2, this is 3, this is 4. That's if you are using numbering. That's why we say it's 3-bromotoluene. But if I want to use alphabets, I said if you know the origin, the next to that origin is the auto. Next to the auto is the meta. On the 4th position is the para. So what will you call this compound now?
Meta-bromotoluene.
Very good. Meta-bromotoluene. toluene. If you put that under oxidation, the oxygen inside the square bracket is a sign for oxidation. You can see what will happen here is this changing to carbonium ion. Why is CH3 going to CH2? Why do we say it's an oxidation? Somebody help us.
There's removal of hydrogen.
Very good. It's removal of hydrogen because you are going from 3 hydrogen to 2 hydrogen. Very good. Very good. And it's also, in terms of electron transfer, it's also the loss of electron because you are going from oxidation state of 0, which has no charge, to oxidation state of +1, which means it has lost 1 electron. And you know oxidation means loss of electron. Reduction means gain of electron when you are talking about in terms of electron transfer. But when you are talking about the atomic content, oxidation means addition of oxygen or removal of hydrogen, while reduction means addition of hydrogen and removal of oxygen. That was very good. Thank you for that attempt. Okay, so let's look at this. There are some other reagents that can help us do that conversion. You can see here we are using cobalt acetate and manganese acetate in the presence of molecular oxygen. That one will still achieve the same oxidation, turning CH3 to COOH. So let's look at this. I want somebody to help try. What's the name of this compound?
Toluene.
Toluene, very good. When toluene was oxidized, it gave us this product. What's the name of this product?
Benzoic acid.
Wow, that's nice. So you know that's benzoic acid. Good. Now, let's look at one that have 2 methyl group. Can somebody help us to name this compound? And you are using molecular oxygen in the presence of cobalt acetate or manganese. It's a strong oxidizing agent that even with 2 CH3, it oxidizes both of them to carboxylic group.
Paramethyl toluene.
Methyl
toluene.
Very good. Paramethyl toluene. That's good. Okay. So the oxidation with molecular oxygen in this acetate group gives us such product that we have here. So in a summary, if you want to note how transformation can happen on Iran group, although Iran cannot be easily ruptured, I told you that 3 double bond inside of it is very stable because it's in alternating manner. Double, single, double, single. It's not like alkene that can easily have addition reaction. But the group that is attached to that arine or benzene group can be transformed. So if you know this single logic, then you have already summarized all the things here. What I'm trying to say is that if you have X being any of these things under this group, if you are treating it with a reagent, these are the reagents under this group, it will effectively convert the X to the Y. Isn't what I'm trying to say is this. If you have toluene, it will have amounted to, if you have toluene, right? It will mean that your X is what? Is CH3. Because you know this is attached to benzene, this is attached to benzene. I am saying that in a summary, I want to pick the first one to explain what we are saying. In a summary, I want to pick the first one. We are saying that if you have this, in which your X is a CH3, and your desired product which you want to get is this. CCl3. What I'm saying is that the reagent you will need to use to treat this is chlorine gas / phosphorus pentachloride. So that's the essence of this. If you are treating CH3, which is methyl group, as your X, and you want to get CCl3 as your Y, the reagent you will need to use is this. Now, let me ask this question. What will you treat with this? Looking at the table that I just gave you about X, Y, and the reagents, look it carefully and use it to answer this question. I want to convert nitrobenzene. Nitro means NO2. I want to convert it to aminobenzene or aniline. Aniline is a benzene ring that have NH2 group attached to it. If I'm asking anybody that, how can you transform nitrobenzene to aniline, what will you do?
You use tin and hydrochloric acid as reagent.
Very good. Tin in HCl. So once you master this table, you have a lot of synthetic transformation will be easier to do, because you remember the course is about organic synthesis. An organic synthesis is about transforming from one functional group to another to get much more relevant compound. If you have a corrosive salicylic acid that is not good to our skin, should we leave it like that, constituting nuisance forever, when we can just change the OH of that salicylic acid to acetate group, and with that alone, you have converted salicylic acid to aspirin, which is a very good analgesic. This is the importance of organic synthesis, looking at compounds that are not beneficial and synthetically modify them at their functional group to achieve a better useful agent. Like salicylic acid now, you cannot consume it, you cannot do anything with it, but just acetylation of that salicylic acid at its phenolic group, just by adding acetic anhydride, we turn it to aspirin, which was one of the drugs that saved the life of majority of people during the Second World War. Until today, aspirin has been a strong and highly valuable analgesic for pain relieving and for treating some other things. So the essence of an organic synthetic chemist, if you are careful enough to understand this thing, you are laying good foundation for yourself, even for the future. If you want to be a pharmacist or pharmaceutical chemist, people that are synthesizing drug, these are all the things they are using, transforming from one functional group to another by knowing what is the reagent should I add. So if I'm saying I need aniline to do some things, and I have nitrobenzene, and nitrobenzene is not useful for me, what can I do? You as a synthetic chemist, you can just say, if you can give me just 0.1 gram of thing and then about 1 ml of HCl, I will give you your aniline. So you just take that thing, and that's the essence of this summary I put here. It will help a lot if you have a grasp of what we are trying to say there. Like for example, if aniline wants to go, you want to turn aniline to a diazonium compound, it's easier. You just treat it with ONO. You treat it with ONO. ONO is an organic acid that is not stable. You can use it to get anything in that format. So if you look at that, let's try and look, because we are about to run out of the time. Let's try this exercise. How can you convert benzonitride to benzoic acid? You see what they are trying to say here? Benzonitride means a benzene that have a nitride group. Benzonitride is a benzene that have a nitride group. How can you convert it to benzoic acid? A benzoic acid is a benzene that have oic acid. You know, oic acid means carboxylic acid or alkanoic acid. What we are asking simply here is this. We are saying you want to move from here to here. What reagent will help you to achieve that aim? That's the question. That's the question. If you go back, you will see that hint of what reagent you need to use. Show with the head of equation the oxidation of paraxamine to dicarboxylic acid. You know what paraxamine is? Paraxamine is like para-methyltoluene. I've told you when methyl group are added to benzene, apart from their common name, they can also have their unique name. You know this one's supposed to have been methylbenzene, but we call it its own unique name called toluene. Now, when you have another methyl group on position 4, we should have called it para-methyltoluene, or we should have called it 1,4-dimethyl benzene. But it also has its own unique name anytime methyl group is attached to benzene. So when you have two methyl group are 1 to 4 position to each other, when methyl group attached is called, if two of them are attached, is called xylene. So if one is attached at the para position to the other, it's called paraxylene. If one is attached to the other in auto position, it's called autoxylene. So this is a paraxylene, that's what they are saying here. How can you convert paraxylene to dicarboxylic acid? To dicarboxylic acid. How can you do that? Dicarboxylic acid means the CH3 hop has turned to COH and the CH3 on position 4 has turned to COH. Can anybody remind us? We've talked about this. We said that if you are using molecular oxygen in the presence of cobalt acetate, you are going to be getting, I said it's a strong oxidizing agent, so it will oxidize both CH3 on position 1 and CH3 on position 2 to form this dicarboxylic acid. So let's go back so we see what we are talking about. Let's go back and see what we're talking about in those two questions. The first question they are talking here is that how can you convert benzonitrile to benzoic acid? You remember what they are adding to that benzene is N and C. If you put this one where X is, what you have there is your benzonitrile. How can you convert it to benzoic acid? If you take this one to where the Y is, that's benzoic acid. So what reagent will you need? You will need alkaline in water. It can be sodium hydroxide, it can be potassium hydroxide. The ionic form of it is OH minus. So aqueous potassium hydroxide or aqueous sodium hydroxide will convert your benzonitrile to your benzoic acid. That's the first. Then the second one, we talked about CH3 in 1 and 4 position. How do you turn them to dicarboxylic acid? This is it. This is paraxamine in the presence of molecular oxygen and cobalt acetate or cobalt and manganese acetate. It turned this one to carboxylic, it turned this one to carboxylic. So that's all we have for today. So I want to appreciate you for your rapt attention for this class today. So while we meet next week, Tuesday by God's grace, but before then, I will have put on the video link and the course material you need to just watch and then pinpoint your challenges that will be there. Then next week we can look at it together. So I believe that maybe next week we have a larger class so that we can fix 1 hour extra that we missed last week. So thank you very much. Do you have any questions from anyone?
No question.
Thank you, sir.
No question. Thank you very much. And I hope to see you next week by God's grace.
Amen.
The same